This course is about modeling in statistics, with connections to algebra, geometry, calculus, and probability. When we do descriptive statistics, you'll be developing sensible ways to operationally define concepts such as the productivity of workers, the friendliness of students in a school, or the accuracy of darts players in the simulation below. Operationally defining such concepts means defining them in ways that are measurable, and usually, this will mean developing some kind of formula. In particular, in statistics, you'll be operationally defining characteristics such as centrality or spread, which are associated with collections of data. Then, when we do inferential statistics, you'll be using Tinkerplot software to develop simulations of situations which have uncertain outcomes. For example, this simulation shows results when 4 darts players play a sequence of games in which each player throws 3 darts. In such a situation, your first task might be to develop a formula to measure the accuracy of each player's throws for each round of the game. Then, your second task might be to investigate how the players rank over a large series of games. This first task is descriptive statistics, and the second task is inferential statistics, because the results of any given game are uncertain. Yet, it is possible to make educated guesses about the frequency that certain results will be likely to occur over a large number of trials. These methods of using simulations to make statistical inferences are often referred to as Bayesian or Fisherian methods, and, to create them, you'll need to be able to build your own mathematical models of the problem-solving situations you investigate. In this course, you'll see that every statistical procedure presupposes a model, and this model embodies assumptions that are made about the quantities, relationships, actions, and patterns that you want to investigate in a given problem-solving situation. This course is organized around 10 or so model development sequences, each of which focuses on one of the big ideas in elementary statistics. As you work on problems associated with these model development sequences, you'll develop your own how-to toolkit for dealing with important types of problems. And this concept analysis wheel can be used to classify relevant goals and basic ideas associated with each tool in your kit. Each model development sequence consists of 6 to 8 40-minute class periods worth of work, plus 35-minute homework assignments. The core of each model development sequence consists of 2 or 3 model eliciting activities, or MEAs. These MEAs are simulations of real-life situations where statistical reasoning is useful. Usually, they require at least 1 full class period to complete, and, for the first stages of model development, you'll be working in teams with 3 students in each team. Why work in groups? It's true that flawed statistical analysis could result from a flawed computational error in some prefabricated statistical procedure, but, more often, flawed analyses result from underlying models which make assumptions that are inconsistent with those that should apply to the situation you're investigating. In this course, you'll learn that every model is useful over simplification of the situations they describe. So, every model is too simple for some purposes, and usually, there are trade-offs between factors such as risks and benefits. So, above all, what you should learn in this course is how to develop your own statistical models for a variety of common problems, and how to analyze and critique models that are produced by others. So, follow-up activities to MEAs will help you develop more effective ways to visualize, generalize, and empower the models that you or others develop, and working in teams to co-develop models will help you develop your abilities to describe, plan, monitor, assess, explain, modify, and adapt powerful statistical tools. Nonetheless, in this course, you'll also need to demonstrate your understandings of group-developed tools in problem-solving situations where you'll be working on your own. And basic skills are not neglected. In general, Activities that occur in class include only those that depend most heavily on student-to-student interactions or student-to-teacher interactions, and anything that involves only the one-way transmission of information will be relegated to homework, to be done outside of class. In particular, to introduce many of these activities, many lectures will be available in YouTube videos like the one you are watching now. In model development sequences, virtually every activity was designed to produce documentation about deeper and higher order understandings than those that are measured on standardized tests. And also, all components of the program were modularized and designed to be easy to modify, extend, contract, revise, or reorganize in a variety of ways. For example, here is how the course has looked when we reorganized it for use with university students, where the class periods can be 90 minutes in length, and where 2 hours of homework is not unreasonable.